to my talk today about decoding the secrets of the JVM internals. I'm very happy to be here today. Thank you all for showing up. I hope you're looking forward to this. I certainly am. This is one of the things I've wanted to talk about for quite a while, so I'm very happy to be here today and share all of this with you. What I'm going to talk about in this session is I want to talk a little bit about what happens not in Java as a programming language, but in Java when you actually run the program. So we're going to talk about what happens at runtime inside of the virtual machine. This is a little bit of like an intermediate, maybe even advanced topic, but I will be going through a lot of the basics. I'm sorry if you're already familiar with some of the things I'll be talking about. I'll try to go through them relatively quickly. I have a lot to go through and not that much time, so let's get started. My name is Lennart and Wolde. I'm a software engineer at Chillit. We're a sponsor here today. I currently work at KPN IoT doing IoT development in Java, mostly or actually entirely backend. So we're working with complex data from millions of devices. That's very exciting. This is the agenda of what I want to talk about today. So as I said, I want to talk a little bit about the JVM internals. My goal is kind of to help inform people so you have a better idea of what's happening in your application at runtime, and maybe give you some recommendations, help you understand some low-level things in the JVM a little bit better. But I think in general, just have a better idea of what's going on under the hood and seeing how that fits into some of the upcoming features in Java. Maybe you've had trouble in the past where you've changed a configuration parameter on your garbage collector and it suddenly got a lot slower, you didn't know why. I want to give you some insight, but of course the idea is that this is something that you build on yourself. So we're going to start with a little bit of an explanation of what the JVM is, what it consists of. Then we're going to talk about memory management and how that works in computer programming languages in general. This will be a relatively quick recap. We're going to look into Java garbage collection, which is an essential part of the virtual machine. I'm going to give you some recommendations on how you can tune your own program at runtime that might be useful to you. And then we're going to take a really short look into how this all fits into the future and some of the upcoming features in Java. So starting off with the JVM, as I said, I hope that most of you are at least familiar with some of the basics of what the JVM is. Obviously, you should know what Java is, but I assume all of you do, but also what the Java development kit is. So, of course, the toolkit of the different tools that you use to take your program from source code to runtime and eventually running it, as well as what the virtual machine is, at least at a conceptual level, but I will recap it for you very quickly. To try and put this in perspective, I have made this graph a little while ago. There is a small typo. If you spot it, try not to see it. We as developers write source code, and one of the tools provided in the Java development kit is the compiler, Java-C, which takes your code, your source code, and it parses it, and then validates it, and eventually produces bytecode, which we typically find in archive files like jar files. Then at runtime, so this is what we're going to focus on in this presentation, this bytecode is taken and it's sent into the virtual machine. Hotspot is the default implementation. There is another one called OpenJ9, but that won't be the focus for today. This hotspot virtual machine contains lots of different tools, an interpreter, which actually interprets your bytecode and turns it into machine code, as well as a JIT compiler and other essential mechanisms like the garbage collector and thread scheduler that is necessary for your program to work. This is a little bit more of an advanced picture that shows all the different building blocks inside of the JVM. So you have different areas that reside in memory, and you have your execution engine, which we'll talk about a little bit, but you can see it consists of many different parts that play together. The first one that I really want to focus on is the interpreter. So when Java code runs, it always starts in the interpreter, which is something not everybody knows. But the interpreter essentially is an abstraction of the CPU. And the reason Java uses this is the idea is you write your code once, You compile it to bytecode, and it needs to run on every machine, on every CPU, and on every operating system. But every CPU is different, has a different set of instructions available, and these instructions are relatively low level. Sometimes only a subset of them is available. So the interpreter essentially acts as an abstraction where the bytecode explains in binary format what your program has to do, and the interpreter will convert this into the correct CPU instructions. An important thing to know about the interpreter is that it interprets these instructions one at a time. So it will look at each instruction, check what it has to do, and then execute that change. And this results in somewhat reduced efficiency, which is why many scripting languages that also rely heavily on interpreters are also a bit slower. And to solve this problem, Java includes a just-in-time compiler. A lot of people know about this from things like JavaScript V8, which relies very heavily on this. Java does so too. In fact, it has two of them, C1 and C2. They compile your bytecode into machine code. And a big difference between the JIT compiler and the interpreter is that the JIT compiler takes multiple bytecode instructions, think like an entire method, like maybe your main method, and it will convert all of those instructions into one block of machine code, which does all of the logic inside. And this creates the opportunity for the compiler to perform platform-specific optimizations. It can do things like inlining and a lot of things that are typically associated with more low-level languages, and it does it all for you so that the developer doesn't have to think about it. Let me go back one more time. Apologies. And it also now reduces the overhead because not every instruction is no longer checked separately. The entire method has been converted into machine code that can run directly on the CPU. This is a key part of the performance of any Java program, right? The architecture of the interpreter and the just-in-time compiler. The just-in-time compiler optimizes your code after it's been ran a while. So maybe if a function has been called 1,000 times or 10,000 times, the just-in-time compiler will optimize it as the program runs, so Java gets faster as it runs. But another key part of performance is memory, because memory is how quickly you can access data, which you do all the time, right? When you allocate new data, when you update data, or when you even read data from objects that you've allocated. And most of you will at least know that I/O operations that go over the network are much slower than when you're just writing to data in RAM. But at a low level, the pyramid or hierarchy of memory latency, as I like to call it, looks a little bit differently. Of course, we have our hard disks, which are very slow, but provide us with a lot of persistent storage. So this is often where we can save and load data from once, maybe at startup. And then we have RAM. And this is pretty much the limit of what you have to think about as a developer. RAM is much faster, but it's actually still quite slow. Querying data from RAM can take several CPU cycles. And all of this time, your application could be doing the work it has to do. So to improve the performance, your CPU contains a cache and a register. And this is not something you interface with as a programmer. It's just something that the CPU does for you. And the cache essentially contains a small subset of your RAM that the CPU thinks you're about to use, so that if you query this data, it will be much faster. And now that you know there's these different layers, you can probably already tell there's plenty of opportunity for performance improvement. And that's a lot of what the JVM does for you. So how does the JVM manage this memory for you? Because we've talked a little bit about the different tiers of memory performance, but where exactly does memory go? Well, there's two places where memory go. It's the stack and the heap. The stack is kind of the content that you're currently using. So if you have a thread, like your main thread that's running, and it has a bunch of variables it's declared, those variables will reside in your stack, as well as any primitive data types. And when you allocate a new object, a reference to that object will be declared as a variable, reside on your stack, and the object itself will be created in the heap. A big advantage of the heap is that this data can be shared outside the scope of a method. But this can be a little bit complicated, so to try and illustrate it, I just wanted to give you a little bit of an example. The stack with memory allocation is like a pile of books. It's very easy to add things on the top, and you can take them off in bulk, and it allows you to manage memory quite efficiently, because each time that you're in a method and you enter another method, you enter a so-called stack frame, where you basically place a marker at the top of your pile. And then when the method is done executing, you can simply remove everything from the top until you reach the marker, and you've now cleared up all of that memory. So memory management is very efficient, very simple, and deallocation is very easy. Because the stack tends to be very small, the maximum size is usually a few dozen kilobytes. It also often resides in the cache, making it much faster at execution time. This is kind of what it looks like. So here you can see each of these stack frames are different method calls being made from the main method at the very highest level. And one way that you've probably worked with this is through stack traces. Stack traces show you every single frame and which method corresponds with that frame, and you use that to kind of trace where an error occurred in your program. But this is kind of the representation of how that looks in memory. So in native programming languages like C, allocating data on the stack is how data is allocated by default. So if you create a function where you just assign a new integer called x, this is allocated on the stack. And in this case, if you run the program, you first allocate one integer onto the stack. You then enter a new function. So you go into a new stack frame where you allocate a second integer. And then when func1 is complete and you go back to your main method, x will be deallocated because the function is done. It's over. You're now back in the main function, and only z now remains on the stack because x can no longer be used. And you'll see that in C, you don't have to manually deallocate this type of data because it resides in the stack, whereas you do if you allocate on the heap. So I've talked about it a little bit. This is a recap. The stack has an advantage because it allows you to do automatic deallocation. It helps you prevent fragmentation because data is managed as a pile, and then when you take data off and then put it back on again, there's no gaps, and it allows for good cache utilization, so it has very good performance. And then you have the heap. And if the stack is like a pile of books, then the heap is like a library where you have lots and lots of data. And when you want to allocate a new object that maybe you want to pass around or share, or really any object at all in Java, it's like you have a new object you're putting somewhere which has an address. So think of that as maybe the specific shelf and the specific row that the book is in. And then you ask the library administrator, where can I put this book, or where can I find this book? So the heap works with it's a very large collection of objects that each have an address, and they're automatically managed for you. So in native code, heap assignments look like this. You're creating a pointer by using the asterisk sign. You're assigning data to it, and unlike with stack allocations, you have to tell when this data has to be deallocated. This is called manual memory management, because when data is shared on the heap, it can be passed around freely, and you have to manually deallocate it. So recapping this and kind of pulling it back to Java, in Java, the stack contains, per each thread that's running, the primitives that have been allocated, as well as references or pointers to the objects that you've created. And that's it. Java does not put objects directly onto the stack. Each object has identity, which means it is not the same as an identical object with different data inside of it, because the identity of an object is essentially the address of where it's located on the heap. And the heap contains all of your objects. So Java makes it pretty simple. But then there's the question of, all right, well, it's pretty easy to figure out how Java allocates new memory. That's when you create a new object. But what about deallocation? And that's where memory management comes in. So in this section, which is relatively short, I'm going to talk a little bit about how memory management works in general in programming languages. I've already talked about manual memory management. You allocate data and you tell the program when it has to deallocate the data by saying delete the data at this pointer. Of course, this has many potential pitfalls. You get maximum freedom, so you can really make it as fast and as convenient as you desire, but you also have maximum responsibility. If you forget to clear data from memory, you create a memory leak, and if you try to deallocate data twice, it can cause unexpected behavior. And this is why Java did not choose this route of memory management. A second strategy you often see is reference counting. Now, in reference counting, when you allocate data, you create a special type of pointer that also includes a count of how many times it's currently being referenced. And then when you're no longer using it in a specific place, you can reset the counter. And when the counter reaches 0, the data is deallocated because it's no longer used anywhere. Now, this can still be somewhat difficult to use. And one thing to note is that it can result in a slightly reduced throughput because your functions now have extra code in them to maintain these counters and check if they are now 0 and then deallocate code. And this is all extra logic that has to be performed, so that's in the way of your actual application logic. But you do see this quite often. And one of the ways reference counting is quite intensively used is automatic reference counting. So the compiler can also insert the code that keeps track of these reference counts and clears the data when it's no longer being referenced. And this way, you can no longer accidentally expose yourself to memory leaks for the most part. And you still get behavior that's very similar to a manually managed application, where the memory is pretty much only exactly what you're actually using. One language that does this is Python. Another one I happen to know of is Objective-C and Swift. Are also now, I think, the only supported strategy is automatic reference counting. But there is a big caveat with this as well, which is that you are exposing yourself to reference cycles. So what are reference cycles? Let's say you have two objects, a human, which owns a number of pets, and it's referencing these pets. So when this human exists, the pets will always have a reference count of at least 1 because they're being referenced by their owner. But the pet can also have a reference back to its owner. And if this happens, then the pet is always referencing the owner, and the owner is always referencing the pet. So even if these objects are not referenced anywhere else, because they're referencing each other, they will never be freed. And this is called a reference cycle. And this can be quite a complicated problem to deal with. And many programming languages solve this by actually including a separate garbage collector which takes care of this. And that also brings us to the last part of the slide. The last way memory is typically managed is garbage collection, which is simply a process separate from the mutator. That's the code that mutates memory. So really, it's just your application, because as your application is running, it's allocating new objects, it's reading from them, and it's, importantly, writing to them. And this process finds and removes unreachable objects. So what does that look like during the life cycle of your application? The mutator, so your own code, allocates new objects as it's doing its thing. If you have a web server, your web server's running, requests are coming in, and new objects are being allocated, until eventually the JVM runs out of memory. Because if you only allocate new data, at some point you run out. Maybe you have 2 gigabytes of heap space. Eventually you're going to run out. Now your application pauses. It stops doing anything. And this garbage collector process starts clearing up the objects that are no longer used to make room so that your program can now continue running. And this continues on in a cycle. Pretty much every garbage collector that I think is currently being used is a tracing garbage collector. And this works by finding objects by tracing references recursively from the root. So I talked a little bit about stacks before, and they contain references to all of the objects that you're using in your current thread, where it's currently running. What the garbage collector does is it will follow each of these pointers to find which objects you're using and mark them as, hey, this one's being used. So it will be marked as live. And then the ones that haven't been marked, when it recursively goes through all of these references, are considered dead. And then afterwards, it sweeps through the memory one more time, and every object that has not been marked is live. So this is data that your program is currently using. It will remove that memory and make it available once again. This is called mark and sweep, and pretty much every garbage collector is based fundamentally on this principle. It looks like this. So at the start, your heap is it's full because you have all these live objects, and there's no more room for new objects to be allocated. So your application is paused. It's going to start marking them, and when marking is done, you know which objects are being used, which are not, and the ones that are not used can then be freed. All right, now we're going to focus back on Java again. So Java exclusively uses garbage collection for memory management, and there's 5 of them that are available. I want to go over each one real quick, tell you what the differences are, and then we're going to give you some recommendations and talk about how they fit into some of the new upcoming features in Java. But before I do that, I need to explain generational garbage collection, because in Java, almost every garbage collector is generational, and this is an important detail to be aware of. So what is generational garbage collection? You now understand mark and sweep garbage collection. Generational garbage collection works by separating objects based on how old they are, right? Generations is much like human generations, where you have boomers and zoomers. Objects can also be divided into similar generations, where the oldest objects are located in a separate area from the youngest objects that were just recently created. So when a new object is created, it goes into Eden space, which is the place for new objects. And then if a garbage collection cycle runs and it's still considered live because it's still used, it's moved to survivor space. And it stays in there until it's survived 7 consecutive cycles by default. And at that point, it's considered old. And you might be wondering, why do this? What's the benefit of this? Well, the thing is, with most applications, if data keeps surviving, if it keeps still being referenced, it's very unlikely to then suddenly become dereferenced, right? If you have a service that you're using, or a cache, or any of your application classes, your Tomcat server, these objects are going to stay in memory and they're not suddenly going to go away. So because of that, you can now create an interesting performance optimization where when the garbage collector runs and you spot one of these old objects, you stop looking because you're just going to assume, hey, this object will still exist. I'm wasting my time. I don't have to recursively go through this and mark all of these objects. I only care about clearing recently created objects, because most of the memory we allocate are things like objects we create during a web request. And these objects are very short-lived. By the time the web request is over, they're no longer needed, they're gone. So by focusing efforts in this area, you can find the largest amount of objects that are no longer being used, and you don't have to scan as much of the heap. There's a bit more to this, but because of time, I stripped out a few slides. Although, of course, you can, if you want to know, you can just search about this and learn a little bit more. So let's talk about some of the first garbage collectors that exist in Java. You have the serial and parallel garbage collectors. These are both simple generational garbage collectors. The key difference being serial garbage collector uses one thread, so your application runs until it runs out of memory, pauses, and now it's going to do the marking and then sweep through the memory to free up unused space so your application can continue running. Whereas parallel tries to split up this work across multiple threads so it finishes faster and ultimately improves the throughput of your application. Throughput, of course, being really the amount of time your application is doing effective work and not collecting garbage. And throughput, for instance, in an HTTP server would be the amount of requests per second, because that's truly the amount of useful work you're completing. So that's serial and parallel garbage collector. Parallel garbage collector is very suitable because it's optimized for maximizing the throughput. So if you want to have the most amount of work done over an extended period of time, that's the metric that that garbage collector was optimized for. But there are some problems with it. Namely, if you have a very large live set, so if you have a lot of objects that are considered live, that are being used, the marking can take quite a long time. And while it's marking these objects, your application isn't running. So if you have a large live set, the pause times can be north of a second, and maybe it's not desirable if you have an application to sometimes have a latency of 1 second on an API call because the garbage is being cleaned up. Another big problem is compaction. When there's fragmentation in the heap, so when there's lots of tiny little gaps, it has to compact it, so it moves all your data to be consecutive so that there's enough new free space for it to allocate new large objects. And this is extremely slow, and it scales with the amount of data that it has to move. So a big problem with the parallel garbage collector, it doesn't scale that well with large live sets of data, and it doesn't scale that well with very large heaps. So to solve this problem, Java created the concurrent mark sweep garbage collector, but that one has been deprecated and since then removed. So I'm not going to talk about it too much, but basically the idea was you can perform the marking while the application is still running, because they don't really interfere with each other that much. But it still had the problem of compaction, which meant that occasionally it would still pause for a very long amount of time, which was undesirable. This is another slide that explains that compaction. So compaction occurs when there's fragmentation. Here you can see that there's a few objects allocated, but because there's now these odd gaps, there's no more room for a large object to be allocated. And when this happens, the garbage collector has to copy all the data to the front so that there's lots of free space again, and this is very slow. So a new method had to be found, and that became the current default garbage collector, G1, or garbage first. Garbage first is different because it splits the heap up into all these little regions. And by doing this, it allows it to use a type of heuristic, which they call their garbage first heuristic, to try and copy over specific areas where there are not many live objects, so that it can gradually compact your heap incrementally without impacting the performance too much. So here you have different regions. Some of them contain old objects, some of them contain Eden space, so brand new objects, and some of them contain objects that have survived for a little bit. But what this allows you to do is when the garbage collection cycle runs, you see that there's these regions, and some of these regions will have quite a lot of live data in them, and some of them will have very little, which means they have a lot of garbage. And what it will do is it will try to clear out or evacuate the regions with the most garbage, and that's where the name garbage first comes from. And by clearing out these very few objects, which is very fast, it's now, as you can see on the third block, it's partially freed up the heap. And as you can see at the very end, even though it hasn't fully defragmented, there's now lots of little empty blocks where bigger objects can go into. So by using this mechanism, it can essentially gradually compact your heap so that the performance impact is minimized. Another really cool thing that G1 does is mixed collections. So if your old objects are eventually, that area of the heap is full, it has to do a full garbage collection cycle, which can be slow because it has to mark all the objects again. But what G1 can also do is include a couple of the regions from the old generation in a new generation garbage collection cycle, which is much faster. And by doing that, when you use G1 correctly, it should really never have to do a full garbage collection cycle, which will result in much lower pause times. With G1, the pause times are targeted to always be under 200 milliseconds, but they're typically way less than that. Even in quite intensive workloads, I've found it doesn't really go above 50 milliseconds too quickly, which is good enough for most use cases. Then lastly, you have the new garbage collectors, ZGC and Shenandoah. I won't go into too much detail, but these are low pause time garbage collectors. They not only do the marking while your application is still running, but also the evacuation that you see in G1. They're based on the same principle. And running the evacuation concurrently to the application is difficult because you cannot write data to an object that's being moved. So to make this work, they both work with inserting barrier code. And this barrier code basically inserts extra bits of code that check, hey, is this object being moved? And if so, write to the correct location. This can further reduce the throughput. In practice, it often doesn't really do it that much. A lot of optimizations have been put in place, but in a worst case scenario, it can get to be somewhere between 0 and 20%. Although you'll find, if you actually try it out, it's probably not going to be that large. A downside, though, is that as of JDK 17, these are not generational. And the main impact of that is that means the garbage collection takes longer, even though it's running concurrently to your program. So even though your pause times are low, the garbage collection takes long, which means that if your application is allocating a lot of objects, it might not be able to keep up. So with CGC and Shenandoah, you want to allocate a slightly larger heap so that there's enough headroom. This is what these barriers look like. It basically inserts some code into your program. When you're reading data, it performs some checks, and when you're writing data, it performs some additional checks. This obviously slows down your code a little bit. All right. That was quite a lot of information. I do apologize. And a very heavy emphasis on memory management, but I really wanted to do that because it impacts so many different areas of the JVM, and a lot of performance is about minimizing the time it takes to load your data from your objects. So what are some things that you might take away from this that you should actually do in your own application? Well, first of all, use the latest version of Java. You can get a 20 to 40% improvement in both latency and throughput just by updating from Java 8 to 17. This is thanks to all the hard work by the developers who are working on lots of different systems, including the garbage collectors. And you'll find that it depends a bit on the application, but specifically memory management has been vastly improved. And just by updating, you're going to get a lot of benefit. So there really is a good reason to update other than just getting the new features. It really is becoming faster every single iteration. And then I want to talk a little bit about when should you actually change the default garbage collector, G1, if ever. So I ran this benchmark, and I need to give a little bit of a warning. I had to create a pretty crazy benchmark that allocates a lot of objects, because I wanted to make a benchmark that shows this in a real-world use case. So I made a Spring application that serves web requests, but because there's so much overhead associated with serving requests already, it's not really that noticeable which garbage collector you're using unless your application is very aggressively allocating memory. So this does not necessarily represent your average simple application, but bigger applications might find this is kind of what you're going to see. Now, one thing you'll see is that the latency of the parallel garbage collector, which is the longest time it took for a request to be delivered, is almost 250 milliseconds. G1 and CGC are very close together with only a small difference, CGC only being a little bit faster. And this is because the other overhead in web requests. Right? If your pause times are already very short, with web requests, you may not see that big of a difference. So it doesn't suit every single use case. You really want to look, do I actually need this? If you look at the actual pause times, which you can get by enabling the logging of your garbage collector, you can see that the parallel garbage collector had a maximum pause time of 200 milliseconds, which explains why it was a bit slower in the worst case latency. G1 sits somewhere in the middle, 70 milliseconds, pretty acceptable and well below its target of 200 milliseconds. And ZGC is so small you can't even see it. It's less than a millisecond. So this means that your application is really always running. So then, when should you actually change it? Well, I think the default garbage collector in Java is probably fine for most use cases. And you might be a little bit disappointed to hear that. But hopefully, even by understanding just what it's doing, you have a better idea of what your program's doing at runtime. But I do think there's some use cases where it does warrant switching. If you have a batch process, you want to maximize for throughput, and pause times of over 1 second are fine. You can use the parallel garbage collector. If you want pause times to be very short, and 200 milliseconds is not acceptable, you can try using the new ZGC or Shenandoah. ZGC is included in virtually every build, and Shenandoah is not in the standard Oracle builds, but you can get them on Adoptium. They are considered production ready and stable. You might use these when you want to react to, for instance, high-frequency sensor data, and then send very quick feedback to a device. That is a good use case for this. Also, if you're dealing with live feedback, so if you have a live dashboard, trackers, or you have very high-intensity WebSocket traffic and you want that to be as real-time as possible, maybe client applications as well as games and game servers obviously benefit from never really freezing up, which can happen even with G1. The next recommendation is if you experience any problems in Java with memory, it's probably because you haven't configured your heap correctly. So your heap is the amount of space that's available for allocating new objects. It's good to enable logging to see how often garbage collection cycles are running. If they run too frequently, maybe you just need to give more memory. Another thing you can consider is if you've reserved a certain amount of space for your application, maybe you just have 4 gigabytes that's reserved on a cluster for this application, you can set the minimum heap size by -XMS and the maximum size to be identical. And if you do this, it will use all of the available memory, which does improve the performance slightly, because the actual size of the heap doesn't really affect the performance, it's only the size of your live set. And the last recommendation, and this is, I think, one of the most important ones, if you do ever notice strange problems and you think it might be due to memory allocation, enable logging. The easiest way is add -X log :GC to your program arguments, and it will print GC logs to the system out. Or you can log it to a file with the second command, so -X log GC asterisk, which means verbose, so it gives me all of the logs and print it to that file. This file can then be uploaded to other tools like GC Easy, which allows you to analyze and visualize what memory is being used, what your pause times are, average pause times, longest pause times, and help you diagnose problems quicker. So, before we end this presentation, I want to talk a little bit about the future. You now hopefully have a better understanding of what's inside the JVM, how memory management is solved in Java, which garbage collectors exist, but why is it useful to know all of this? Well, there's some upcoming changes to Java. First of all, they're now introducing generational ZGC in Shenandoah. This is already present in JDK 21. To use it, you just pass in the flag -XX + Z generational. And this will allow you to better keep up with very high allocation rates without having to massively scale up your heap. It needs less headroom to work. Shenandoah is also adding a new generational mode, but I believe it's been very recently taken out of JDK 21 because it wasn't quite ready yet. But it's fun to play around with and see how it affects the performance of your application. But really, I think one of the exciting areas is the Java enhancement proposal for value objects. So you heard me talk about objects that have identity, which means they have an address where it resides somewhere on the heap. This is different from other programming languages like C and Rust, where you can actually have objects that don't have identity, they're just blocks of data, and this allows for many optimizations to be created. So Java's introducing this to where you can now, with each class, say whether it's an identity class or whether it's a value class. And if it's a value class, it doesn't have identity, so if you compare A == B, it will not check, does this have the same memory address? It will check, is the data identical, which maybe makes it a little bit less suited for use in hash maps, because that does these checks, and it will slow down a little bit if it has to compare the data. But it does have some major benefits, namely field access will be faster, because the memory loads will be much faster. It doesn't have to jump to some point inside of the heap. It's very likely to be stored in your stack. So reading data can become significantly faster. And it also allows for better performance optimizations in the JIT compiler and the garbage collector. So there are plenty of reasons to do this, particularly if you're doing some kind of big iteration. Using these objects can make a really big difference to the performance of your application. And it's worth experimenting with if you have some performance critical code that isn't directly related to I/O. Also, obviously, because there's less memory overhead and because it doesn't necessarily need an address on the heap, this will improve your cache utilization because it's more likely to be on the stack. And there isn't the overhead that is associated with an object where it needs to be somewhere on the heap and it needs all of this additional metadata. So this will be very fun to play around with. It's not quite there yet, but it's good to have this one on your radar. I think it's one of the most exciting upcoming features if you care about writing performant, sensitive code inside of Java. This is going to make it a lot easier. And that is the end of my presentation. If you enjoyed it or want to talk a little bit more about this, have some questions, please visit us at our Chill It stand. We have a hot sauce challenge as well, and you can get our very own, figure out how to open this, signature sauce, which has an open source recipe. So if you're interested in trying out our hot sauce, you can get a bottle of these for free. So come and say hi, let's chat, and hope you all have a good time at JSpring.